In this video, I'll introduce you to the bivariate normal distribution. Such a joint probability distribution can be used to model pairs of random variables. For example, the joint distribution of body lengths of two women in the Netherlands. First, I present two more Dutch women, my neighbor and my sister. My neighbor and I have rather different heights, but my sister is almost as tall as I am. Here you see the scatter plot of a few hundred adult neighbor pairs. The horizontal coordinate of each data point corresponds to the body length of the neighbor with the highest house number. The vertical coordinate corresponds to the height of the other neighbor. And here a similar scatter plot, but now for pairs of sisters. The elder sister's length is shown horizontally, the younger sister's length vertically. So do you see the important difference between the two graphs? The height of the neighbors do not show any correlation. When I am tall, there's no reason why my neighbor should be tall as well. The variables describing our heights are independent. Sisters, however, often have similar body lengths. The correlation is not perfect, but the upward trend is unmistakable. If a woman is tall, her younger sister is probably tall as well. And if a woman is short, her sister probably is shorter as well. Let's first focus on the sisters. These graphs are the histograms of the heights of the younger and the elder sisters separately. The normal bell shape matches these histograms very nicely, and both variables can be modeled by two very similar normal distributions. For normally distributed variable x with the expected value μx and standard deviation sigma x, the probability density function is given by this formula. Now we want to describe two variables simultaneously. So we need the bivariate version. Are you ready for the formula? Here it is. The joint probability density function of the bivariate normal distribution. Its parameters are μx and μy, sigma x and sigma y, and also rho. Let's first look at the graphs. The joint probability density function is a function of x and y. So its graph is a surface in 3 dimensions. It has the bell shape of the normal distribution both in the x and in the y directions. The integral of the PDF over R2, so the volume under the surface, is 1. And this is a graph of the level curves. This is quite a good match to our scatter plot, isn't it? Back to the formula. Let's see what the parameters mean and how we estimated them. μx and μy are the expected values of x and y. We estimated those from our bootstrap dataset by their average values. Similarly, sigma x and sigma y are the standard deviations of x and y, which were estimated by the sample standard deviations. Finally, rho is the correlation coefficient. Rho can also be estimated from the data. Here we found rho hat is 0.52. What is the role of rho in this joint distribution? We now use standard mu and standard sigma values of 0 and 1 and change the rho. This is the probability density function for rho is 0.82. The correlation between the two variables is even stronger than in the sisters case. The negative rho value gives joint distributions where large values for x lead to smaller values for y, and vice versa. For pairs with small x, you would expect larger y values. A special case is when rho is equal to 0. Then there is no positive or negative trend in the data. We have used the rho of 0 to model the body lengths of pairs of neighbors. It is quite instructive to see what happens in the formula when the rho equals 0. If every rho equals 0, a few factors 1 minus rho squared simplify to 1. And the middle term in the exponent vanishes altogether. This has a special consequence. For rho equal to 0, the joint probability density function can be written as the product of a function in just x and a function in just y. The joint PDF factorizes into the univariate normal PDF for x and the univariate normal PDF for y. You know what that factorization means. In the rho is 0 case, the two random variables are independent. Recall that if two random variables are independent, then their correlation coefficient is 0. We have just seen that the bivariate normal is special. The implication holds both ways. If two bivariately normal random variables are uncorrelated, then they are independent. I'll show you the combinations in this table. Two random variables can be independent or not, and they can be correlated or not. First, the general case. If x and y are independent, it follows that their correlation coefficient is 0. If the correlation coefficient is not equal to 0, then automatically x and y are dependent. The PDF here is of a uniform distribution over a quarter circle. There is a downward trend. For large x, the y can only be small. The correlation coefficient is negative, and x and y are dependent. The uniform distribution over a ring is an example of a random variable that is uncorrelated. There is no linear trend in the data. However, x and y are not independent. For example, for x is 0, the probability for small y is 0. In general, for joint distributions, there are three possible combinations of these two properties. In the bivariate normal case, however, independence is equivalent to having no correlation. So there are only two possible combinations. Either it is the neighbor's case, x and y are independent and uncorrelated, or it is the sister's case, x and y are dependent and correlated. In this video, I've shown you the bivariate normal distribution. If you want, you can easily generalize it to a multivariate normal distribution for 3 or more variables. They all have the nice properties of the univariate normal distribution, plus, pairwise, they have this equivalence of independence and no correlation.